Well, hello everyone. I'd like to welcome you to the Human Physiology Kidney section in our series of lectures. My name is Dr. James Scully. I'm a professor of medicine and a physician scientist here in the University of Toronto, and also a physician scientist in the Toronto General Research Institute. I'm a staff physician in the Division of Nephrology at the University Health Network and Mount Sinai Hospital. And so what we'll try to do in the kidney physiology section is relate some of our discussions of basic renal physiology to some clinical settings that we see in the hospital going forward. So just to give you a beginning, the structure of each lecture, we're going to start with a case of the day. This is an example of a clinical problem that's meant to illustrate the practical use of some of the principles that we'll discuss in terms of the renal physiology. And therefore, the clinical problem will be directly related to the lecture topic of that day. And our hope is that that clinical lecture and topic will illustrate the importance of understanding normal physiology so we better understand what happens when physiology is perturbed in the setting of human kidney disease. So, we'll have 8 lectures in this section, and this outlines each of the lectures. And so we'll start off today with fluid compartments. We'll move on to understanding the important role of glomerular filtration rate, and then we'll focus on tubule function. Finally, we'll focus on sodium and the key role that the kidney plays in regulating sodium balance and blood pressure. And then we'll talk about water and how the kidney regulates our water balance and plays a key role in maintaining what we call internal homeostasis. We'll then focus on potassium, particularly as it relates to human physiology. And then we'll talk about acid-base balance and the key role that the kidney plays in maintaining normal acid-base balance in the setting of normal intakes of food and the generation of acid through metabolism. And then finally, we'll return to endocrine functions of the kidney with a focus on a metabolite called urea, which is also excreted by the kidney. Now, just before we start, I thought I'd talk about a recent article in the Journal of Nature, which is to give you something to think about that's kind of fun on the side. In this particular article, they asked, how could recycling urine, which all of us think of as a waste product, help save the world? Now, that's a rather bold statement, and to understand why someone would consider using urine to help save the world, we have to have an understanding of what the kidney regulates and what are the constituents in the urine that are a consequence of that regulation and how they might save the world. So I'll let you think about that, and in the last lecture, we'll return to it and see how our understanding of renal physiology can help us understand how someone might think that urine, a waste product, might indeed help save the world, particularly from an agricultural perspective. So, we'll hope to understand why urine, instead of being a waste product, may indeed be an important product. So, in our launch into renal physiology, I think that we really have to start at the very beginning by embedding our concepts of body fluid compartments and how we think the kidney regulates body fluid compartments and what are the functions of the kidney that influence both the volume and the constituent particles within each of those compartments. So today we're going to focus on body fluid compartments. I'll present a case of the day at the beginning and we'll return to it at the end. We'll define what the fluid compartments are. We'll look at water permeability and solutes. We'll look at the movement of water between compartments and what are the forces that influence movement of water between the compartments, because understanding the distribution of water and what determines that distribution of water between body fluid compartments will give us a key idea about how the kidney works and how the kidney receives signals to influence the balance and maintenance of normal body fluid compartment volume and composition. So here's the case of the day. This is taken from one of my partner's case series. This is called the Seizing Marathoner. So here we have an example of a 45-year-old woman who runs her first marathon after she underwent a series of training runs over 6 months' time. She finished in 5 hours, which is a pretty respectable time, and during the entire race she rehydrated herself at various intervals with water. At the end of the race, she complained of a significant and severe headache. She then went on to feel very nauseated. She vomited. She then had a seizure. She collapsed and she was taken to the medical area at the finish line for attention to her condition. So let's return now to body fluid compartments and see if we can understand how this healthy 45-year-old marathoner who rehydrated herself with water got into all kinds of trouble at the end of a marathon. So here's our notion of body fluid compartments. So in the right-hand side, of course, is a cartoon of a human. And on the right side is a beaker. Now, I've been criticized in the past by students because I often say to them that I actually look at a person and I see a beaker. And what I mean by that is that each and every one of us as individuals has body fluid compartments that make up our total weight. And on the basis of weight, humans are actually 50 to 60% water, which is indicated here in this beaker on the right-hand side. Now, what factors determine body water as a fraction of weight? The first thing to know is that it's actually dependent upon the relative mass of muscle and fat. Muscle is a high water content compartment, whereas fat is a much lower mass of water. So fat has very little water, muscle has a lot of water, and muscle actually contains most of the water in our body. On average, there is more fat muscle in women compared to men, and that accounts for 50% of the total body weight of a woman, on average being composed of water, and 60% of the body weight of a man, on average composed of water. As we age, we lose muscle mass, and so the older an individual compared to a younger individual. So if you were to compare my total body water to your total body water, you'd find that I had a less total body water for a given body mass. And chronic illness also impacts on the volume of water relative to the total body weight. How does it do so? Well, in chronic illness, there's a gradual and sometimes abrupt reduction in muscle mass. And that reduction in muscle mass leads to a reduction in the total body water. So although we think of these figures as 50% in women, 60% in men, there are a number of other influences related to age and health that impact the amount of water that is a fraction of our total body weight. So this table here, taken from your textbook, shows water content as a percentage of total body weight by age and sex, two of the most important determinants of total body water. And you can see that if we start, for example, age is in the first column, males are shown in the second column, and females in the third column. And that at birth, infants are about 65% water. That is, 65% of their total body weight is composed of water. And if we focus first on the second column of males and go down, you can see that as we reach middle age, between 39 and 59 years of age, we settle in males at around 60% of our total body weight is composed of water. And then as we get older, that amount declines, again reflecting the reduction in muscle mass. In females, we start off at the same composition. 65% of the total body weight is made up of water. It rises gradually until teenage years and then declines as we in the third, fourth, and fifth decades, so that again in middle age around 50%, and then in older females down to as low as 45%. So age and muscle mass and sex are the three most important determinants of total body water. That is the amount of water that is a percent of total body weight. So, where is the water? So this cartoon depicts in a very simple way actually the three compartments. Shown here is the cellular compartment. This is the intracellular water. Shown here is the extracellular water, and it's composed of two spaces, an interstitial space and an intravascular space, shown here. So there are in general three compartments in the body in which water is found. It's found in cells, it's found in an interstitial space, and it's found in a vascular compartment. So if we look at this cartoon of a male, for example, here, we can look and see where is that water. Well, we can see here up on the upper left, muscle contains a lot of water. This shows the pectoralis muscle here. And indeed the heart, the myocytes contain a lot of water. If we take a cross section shown here of muscle and look at that tissue, we can definitely see where the cells are, and you can see that there's a vascular compartment here, and then this interstitial compartment, which is the space between the cells. And if we look at the heart, again, we can see a vascular structure. That's the intravascular volume. We can see an interstitial space, and then we can see all of these cells making up the heart. Again, at a tissue level, there's a cellular compartment, an intracellular compartment, an interstitial compartment between cells, and a vascular compartment, the intravascular volume. And if you look with an electron microscopy at tissue, you can begin to see these three compartments. So shown here is the interstitial space, a complex matrix of proteins. And shown here is the intravascular space. And shown here are the cells. Now, of course, in this particular picture, you don't get a sense of the proportion, but it's meant to represent on a colorized electron micrograph at the tissue level what the three body compartments look like. Cellular, intravascular, and interstitial. So that's in general terms. 50-60% of total body weight is water. And that water is distributed into three compartments: intracellular, intravascular, and interstitial. So let's get quantitative and see what that looks like at the level of an individual. So these particular pictograms shown here show the percentage of that total body water. Where is it located? And this represents on this side a woman and on this side a man. So the first thing to note is that the most of the fluids in the body are retained actually here, for example, is that 60% of the total body fluid in a man. And 2/3 of that water is intracellular. So 60% of the total body weight is water, and 2/3 of that water is retained within cells. And we look here, 1/3 of that water is outside of cells. And what are the two compartments outside of cells? The interstitial space and the intravascular space. So that represents about, in this particular example, 80 and 20%. So the notion is that if of the total body water, 60% in a male of their total body weight, 2/3 of that is inside a cell. 1/3 is outside of the cell. Of the 1/3 outside of the cell, it resides in two compartments: the interstitial space, which is the larger compartment, and the intravascular space, the smallest compartment. So that fluid is sequestered in a differential manner. Most is in cells, the next amount is in the interstitium, and the smallest amount is in the intravascular space. So let's look at a graph and get particularly quantitative. So this is the percent of total body water. And we're looking at the intracellular and extracellular compartments. 60% of a 70 kilogram Male is 42 liters, 42. So of a 70 kilogram male, his total body water is 42 liters represented. Of that 42 liters, 28 liters, 2/3, resides within the cellular compartment, inside of cells. And 14 liters, 1/3, resides outside of cells. Now remember, when we think of the body fluid compartments that are outside of cells, there are two compartments composing that extracellular fluid. The first is the interstitial space, some 75 to 80%, and the other is the plasma compartment, some 20 to 25%. Again, showing us that if we know the total body water, we can see that the 2/3 is inside the cells, 1/3 is outside the cells, and outside the cells, about 3/4 sits in the interstitial space, and 1/4 sits within the intravascular compartment. These are important numbers, and these concepts will return as we talk about the regulation of water and the regulation of sodium in subsequent lectures. So this represents a pictogram again, but it shows something that I'll come back to occasionally through the following lectures. It represents, if you like, a beaker. And within that beaker, there's water. And within that water, 2/3 sits inside the cell, 1/3 outside of the cell. 3/4 of the water outside the cell is in the interstitium, and 1/4 is in the fluid compartment. Important, key, fundamental ideas about body fluid compartments. And we're going to see how the kidney responds to signals in terms of the amount of water inside cells, and particularly the amount of water inside the vascular compartment. So, what determines water permeability and the movement of water between these compartments? So let's talk about that for a few moments. Water permeability. So cells are surrounded by a lipid bilayer, and that lipid bilayer does not in fact confer permeability, but cells are permeable to water. So water can move from the extracellular compartment into the intracellular compartment. But how does it do so, and how is it regulated? So the first thing we have to know is that a lipid bilayer is impermeant to water, but water permeability is provided by a number of integral membrane proteins that as a family are called aquaporin. Now, if you think about it in Latin terms, aquaporin is a water pore. And aquaporins, as a family of integral membrane proteins, confer water permeability. And you can see the molecular structure. These actually have many components to them, and they provide a channel that allows water to move across a cell membrane to the other side of that cell membrane. And we'll talk about what determines that ability of water to move. So aquaporin channels provide an avenue for the rapid movement of water molecules across plasma membranes. At least 10 different aquaporins are known in humans. And as an example, in terms of the quantification, each individual red blood cell is felt to have 2 × 10⁵ copies of aquaporin inserted into its cell membrane, conferring water permeability and enabling the rapid movement of water from inside the cell to outside or outside the cell to inside. The channels allow for the bidirectional movement of water. Proximal tubule cells within the kidney that we'll come to in lecture 3 actually have 5 different types of aquaporin proteins conferring permeability in the cell membrane. Now, these are celebrity proteins. Indeed, they were discovered only 30 years ago in 1990. And this represents a lipid bilayer, shown here, and this represents the multi-component aquaporin channel. These represent water molecules, and water molecules can move through the aquaporin channel across the cell membrane. And this represents, of course, the lipid bilayer, which in and of itself is impermeant to water, but it's the integral membrane proteins that are inserted into that lipid bilayer that confer the permeability of water to that cell membrane. Indeed, this is such a fundamental mechanism by which water is transported across cell membranes that it led to a Nobel Prize in 2003 for the scientist at Johns Hopkins University in the United States who discovered and then described the aquaporins in much more detail. When I was a renal fellow training, we didn't know about these proteins, although we absolutely knew that water permeability was conferred by proteins. We just didn't know what they were. So let's talk about solutes. And what are the dominant solutes, the small particles that exist within the body fluid compartments? Now, a few definitions just before we go forward so that we understand and try to remain fairly true to our language. So solutes are particles dissolved in water, and the three ones that we will focus on are sodium, potassium, and a little bit later in our lectures, glucose. These are small water-soluble particles. Ions, of course, are charged solutes, and the cations are positive, anions are negative. So sodium and potassium are the dominant cations or positively charged solutes. Osmolality is the concentration of solutes in water that generates an osmotic force. So, what is an osmotic force? Well, shown here is something you might have thought about maybe even in high school chemistry. So you have a U-tube here, and we have a semi-permeable membrane just at the bottom of that U-tube. And on one side we have a solution with 6 particles. On the other side we have a solution that has about 10 or 12 particles. So the solute concentration is different. The osmolality in this compartment is greater than the osmolality in the left-hand side compartment. And that difference in osmolality confers an osmotic pressure that drives water to move across that semi-permeable membrane. And so water will move down, if you like, a concentration gradient across a semi-permeable membrane to equalize the solute concentration, to equalize the osmolality. And this difference here is actually the osmotic pressure. It's important to realize that the concentration of solutes that confer osmolality to a solution lead to a gradient that regulates the movement of water across cell membranes. In this particular example on the left-hand side, cells can't tolerate an osmolar gradient across the cell membrane, and water will move from this compartment of a lower osmolality to another compartment of a higher osmolality through aquaporin channels to normalize, or at least make sure that the osmolality is similar in each compartment. And we'll come back to this. So, osmotic force. The osmotic force is a movement of water across a semi-permeable membrane, like a cell membrane that is a lipid membrane with it has aquaporin channels inserted in response to an osmotic gradient. The osmotic gradient is the difference in the osmolality of the compartments. And water moves from the compartment with the low osmolality to the compartment, misspelled here, with the high osmolality. That's a key point to understand. Water will move from an area of low osmolality to an area of high osmolality, so that it always attempts to normalize the difference, or in other words, equalize the osmolality across that semi-permeable membrane. So we come here, this represents the cell membrane in our particular U-tube. And in the U-tube, as in a cell in the body, that cell membrane will enable water with the aquaporin channels inserted to move from low to high osmolality and equalize the osmolality across the membrane. Now that's the sort of chemistry, if you like, about it, but it's an important point, and it leads to this question. Is the osmolality the same in all body fluid compartments? Now, there may be subtle differences, and we're going to return to one of those important differences later on in our lecture series, but a general rule: the osmolality in all body fluid compartments is equal. That means that if you and I could plant ourselves inside a cell, inside the interstitial space, or inside the intravascular compartment, we would find as we looked around us that the number of solutes per volume in that space was equal. And that means that the osmolality in a cell equals the osmolality outside of the cell. If the osmolality was suddenly higher here, then water would move out of the cell. If the osmolality was low here, then water would move into the cell and equalize the osmolality. So that by having aquaporin channels within the cell membrane conferring permeability to water, it renders the cell unable to tolerate an osmolar gradient, and water will move across the membrane bidirectionally to equalize osmolality, and similarly in the vascular space. An important concept, because we'll see how that influences the regulation of body fluid compartment volumes and sodium content. So now that we've determined that the osmolality in all of the body fluid compartments is for practical purposes the same, then the question we have to ask ourselves is, well, what are the solutes in each of those compartments that are contributing to that osmolality? Remember, osmolality is the solute concentration in that fluid. So what are the solutes that contribute to the osmolality, which is equal? Are the solutes the same? And the answer is no. The solutes are not the same in each compartment, although the concentration of the solutes is equal. Let's look here. On the y-axis is the concentration in millimoles per liter. And on the x-axis, there are several bar graphs. The first shows sodium, the second shows the potassium, and we'll focus really on these ones to begin with. And there are 3 bars over sodium and 3 bars over potassium. The first is the plasma or the intravascular volume. The second is the interstitial space or interstitial volume. And the third is the cellular or intracellular volume. So plasma volume, interstitial volume, cellular volume. And what you can see is right away that there's the dominant positively charged solute in the plasma compartment and the interstitial space is sodium. And there's very little sodium, within the intracellular space. And it's the mere effect when we look at the potassium concentration. So when we look in the intracellular compartment, potassium is the dominant intracellular positively charged solute, conferring osmolality. Outside the cell, it's dominantly sodium. And when we look inside of the cell, there's very, very little, outside of the cell, there's very little potassium, relatively speaking. So here we know that the osmolality is relatively equal outside and inside the cell. But the solutes that confer that osmolality are different. Inside the cell, predominantly potassium. Outside the cell, predominantly sodium. And then there are differences in the chloride and bicarbonate concentrations that we're not going to concentrate on now. But the key message in this slide is that although osmolality is the same, the solutes that confer that osmolality differ depending on the body fluid compartment. Inside cells, potassium. Outside cells, sodium. So, cells are surrounded by a lipid bilayer that in and of itself would be impermeant to water but is permeable to water because it has integral membrane proteins called aquaporins. Those aquaporins allow cells and in the intracellular and extracellular space to maintain a similar osmolality. But solute concentrations differ inside and outside of the cells. That is, the solutes that make up that osmolality differ. Their total concentration is the same. So the question now we have is, okay, water can move across cells by virtue of aquaporin channels. How do cells establish and maintain differences in the positively charged solutes that confer that osmolality, sodium and potassium? How is it that potassium is so high inside cells and sodium is so low? And how is sodium so high outside of cells and so low inside of cells? Now, here we return to another ubiquitous integral membrane protein that has multi-components, and this is the sodium-potassium pump. Now, it's called sodium-potassium ATPase because unlike aquaporins, which just provide permeability, they're just like a tunnel through the cell membrane. This integral membrane protein, shown here, inserted into this lipid bilayer, confirms permeability, but it pumps it and it requires energy. So the hydrolysis of ATP to ADP enables this cell to move sodium from the inside in the cytoplasm to the outside to the extracellular space. And as it moves sodium out of the cell, potassium moves in. So you and I have an integral membrane protein, a sodium-potassium ATPase, that sits within the cell membrane and is responsible for maintaining that differential concentration of positively charged solutes within the bodily fluid compartments. Indeed, actually, sodium-potassium ATPase is ubiquitous. It's in all cells. And the other thing that's interesting is that it requires energy. It requires the generation of ATP, and that it plays a key role in consuming ATP, and cells are committed to generate ATP to maintain that gradient of sodium outside of the cells and potassium inside of the cells. So this is a little bit more, this cartoon demonstrates the components, the alpha subunit and the beta cell unit of sodium-potassium ATPase. Here's our lipid bilayer, our cell membrane. Here's the inside of the cell, and here's the outside of the cell. And what this does is there are sodium binding spaces, and there are potassium binding sites, and there's an ATPase hydrolysis site, and the ATPase is hydrolyzed. That confers energy, which allows sodium to move out and potassium to move in. Critical to maintain this gradient, and we'll see how that has important effects on kidney tubule solute transport and how it has critical effects actually on electrical activity in the cardiovascular system. Key protein that maintains that differential solute concentration. So the rules, if there are rules, sodium with an anion is restricted to the extracellular fluid compartment for practical purposes, and it is the main extracellular fluid osmol, confirming osmolality and regulating water transport across the cell membrane. Water crosses cell membranes to equalize osmolality in the extracellular fluid and in the intracellular fluid compartments, but the solutes are different. Sodium outside, potassium inside, dominantly. So, movement of water between compartments. What happens to the intracellular fluid compartment and the extracellular fluid compartment if we drink water, like that marathoner who's running for her 5-hour finish and is rehydrating just with water as she races? So the water is absorbed from the gut into the extracellular fluid compartment. So as that runner is drinking her water, it's going into the extracellular fluid compartment. And when it does so, it lowers the sodium concentration in the extracellular fluid compartment. It just dilutes it. That lowers the osmolality. Now remember, water moves from a space of low osmolality to a space of high osmolality. So if we drink water, absorb it, lower the extracellular fluid sodium concentration, lower the osmolality, the consequence will be that water will move from the extracellular space into the intracellular space. And as a consequence, both compartments will increase. So as this marathoner is jogging along and drinking water, that water will serve to increase the extracellular fluid space. Of course, that dilutes the sodium there, but because water will move across, both compartments will increase, and her intracellular fluid compartment will increase. So let's remember that when we come back to the case. So here in this cartoon example of drinking water, here's a single cell. In this case, it's actually a red blood cell. And here's it on the right-hand side. So in a state in which the osmolality is similar in the extracellular and intracellular space, if we drink water and dilute the solutes outside the cell, water will move into the cell to dilute the interior of the cell, and the cell will expand. Okay? So, drinking water will lead to an increase in cell size. Now that's important when we come back to our marathoner. Why did drinking water lead to so many symptoms like headache, nausea, and a seizure? And it might have something to do with the volume of cells in her brain. So what happens if to the extracellular fluid compartment and the intracellular fluid compartment if we eat salt? So if we eat salt, the salt ends up in the extracellular fluid compartment. It stays there because sodium, potassium, ATPase, if any leaked into the cell, would pump it out. So the sodium stays in the extracellular space. What will that do? Well, we'll put sodium into the extracellular space. It will raise the osmolality. Now, this is the opposite of what happened when we drank water. When we eat sodium, there's an increase in the extracellular fluid osmolality, and water will move from the extracellular space from the intracellular space to the extracellular space. And that will lead to different effects in the body fluid compartment. So eating salt will decrease the intracellular fluid volume, but increase the extracellular fluid volume, and cells will shrink as a consequence. That's illustrated in this diagram, is that when we eat sodium. In this particular example, in the normal osmolality and equilibrium, for every volume, it's equal number of solutes for each volume here in the extracellular, here in the intracellular space. We eat sodium, we load up on the solute particles outside of the cell. What the cell will do is allow water to move through aquaporin channels from the interior of the cell to the exterior or the extracellular space. And when it does so, it will tend to lower the concentration here to try to maintain equilibrium across the cell membrane. So to this point, we've considered the intracellular fluid and the extracellular fluid, which are really just separated by a cell membrane. We said that cell membrane is a lipid bilayer, impermeant to water, but permeable to water because we haven't left the lipid bilayer alone. We've inserted aquaporin channels that confer permeability. And we also know that there's a difference in the solute composition in the extracellular and intracellular space, and that is conferred by another integral membrane protein, which is sodium, potassium, ATPase. So now we have a second question. We've asked several questions, but this is another question at this point. What determines the movement of water between the interstitial compartment and the plasma compartment? Now, the key difference here is that these two compartments are separated by a leaky, water-permeable capillary. So remember, the plasma or intravascular compartment is what's within our bloodstream. And the interstitial space is what's surrounding that between the blood vessels and the cell membranes. And the capillaries are generally pretty leaky to water. So what is responsible for water moving from a vascular compartment or plasma compartment to an interstitial compartment? And that is due to two opposing physical forces. So not osmolality gradients, not differences in sodium and potassium, but rather opposing physical forces. So let's look at a cartoon of a capillary. And so this example, here's our extracellular fluid, has an interstitial component right here, and this is our plasma compartment or our intravascular compartment. And we've said it's pretty leaky, so water moves across, and we know that the solute concentrations are the same everywhere. And we know that the dominant positively charged solute is sodium, and it's sodium outside of the cell. And we know that the osmolality is equal because water can easily move through this leaky capillary. So if we were to suddenly try to push a bunch of positively charged solutes into the blood compartment, water would move out and equalize that rapidly so that no matter where you and I landed, here or here, we would find the osmolality would be equal, and we would find the sodium concentration in general would be equal. There's new data that suggests there's a lot more complexity within this interstitial space, but practically speaking, the osmolality is the same in the plasma or vascular compartment as the interstitial compartment, and for practical purposes, the sodium concentration is the same. Different, of course, if we leap back to the intracellular space, because there, although the osmolality is the same, the positively charged solute is different. It's potassium. So, extracellular fluid compartments, the plasma volume or the intravascular volume versus the interstitial volume. So water flux, the movement of water from one compartment to the other, is determined by Starling Forson. Now, Starling was a physiologist. And what he determined was that water moves from one of these compartments to the other on the basis of the hydrostatic pressure gradient within the vascular compartment or the plasma compartment. And that hydrostatic pressure is generated by the heart. So that's how we have a blood pressure. We have a hydrostatic pressure gradient that favors pushing water from the plasma compartment into the interstitium. And there's also another important point, which is the oncotic pressure. And the oncotic pressure in the plasma compartment is determined by the protein concentration, the concentration of the protein albumin. So the key forces that influence water movement from the capillary vascular compartment into the interstitium are indeed hydrostatic, generated by the heart, and oncotic pressures generated by the protein albumin. Now, the difference between oncotic pressure and osmotic pressure is really a bit of semantics. Oncotic pressure is generally referred by a small concentration of very large particles, and osmotic pressure is generally conferred by a high concentration of very small particles. Similar, though, from a physical chemistry perspective. So, albumin serves to provide an oncotic pressure that keeps water in the vascular compartment, and the heart generates a hydrostatic pressure which tends to move water from the vascular compartment into the interstitial compartment. So a word about albumin, it's the main protein in plasma. Each of us have a concentration of about 40 grams per liter. It's much lower in the interstitium, so it's a big protein. And although those capillaries are very permeable to water, they're not very permeable in their healthy state to a large protein like albumin, which has a molecular weight of 68,000 daltons. So capillaries have a very limited permeability to albumin, and they tend to provide an oncotic pressure that holds water in the plasma relative to the interstitial volume. So now let's look back and we say, well, gosh, we've got those three compartments. The osmolality is the same everywhere. Potassium is pretty much restricted to the intracellular space. Sodium is pretty much restricted to the extracellular space. And in the extracellular space, albumin is pretty much restricted to the intravascular plasma compartment. And the generation of a hydrostatic pressure is also pretty much restricted to the vascular compartment because the heart pumps blood and generates a pressure. So fluid movement across capillaries, said another way, water movement across capillaries from the interstitial space to the capillary lumen, or from the capillary lumen to the interstitial space, is conferred by Starling forces, the hydrostatic pressure, the oncotic pressure, and indeed the permeability of the capillary. So some capillaries will have differential permeability to water, and we're going to be talking about that in our very next lecture. And this is represented here by the flux of water, the permeability, or the permeability coefficient, the pressure gradient, and the gradient between the oncotic pressure generated by albumin. So again, hydrostatic pressure is critical, oncotic pressure is critical, and all of them involving an axis, if you like, between the vascular compartment, the interstitial compartment, the heart, and the liver. So if we come here and look back at our cartoon and wonder about what causes water to move from one compartment to the other, it's on the basis of these Starling forces. If we have a permeable capillary, then the hydrostatic pressure here will push water in this direction into the interstitium. And the oncotic pressure conferred by these large red dots, which are meant to represent albumin, will tend to move water in this direction. So as plasma enters the capillary, it tends to move in this direction as it goes forward, and then it tends to recapture as it goes back. So if we were sitting in the early capillary bed, we would see the Starling forces move water into the interstitium. And as we moved along this capillary, we would find that we would reach a point in which the oncotic pressures began to move fluid back into the vascular compartment, pretty much for a net zero gain. Now, that's not entirely true, but again, for practical purposes, we'll say that there's a net zero gain. That's demonstrated here, in which leaky capillaries allow movement through gaps in the cells. So again, we come back. So this is a bit of a summary slide. Here's our beaker. Here's our intracellular space. Here's our interstitial space. And here's our plasma or vascular compartment. 60% of the total body weight in a male, 55% in a female. 2/3 of the water sits in the intracellular space, 1/3 in the extracellular space. 3/4 of the extracellular fluid is in the interstitium, and 1/4 is in the plasma volume. The osmolality as we jump from one compartment to the other is the same. But inside the cells, potassium, and outside the cells, sodium. And here, albumin, and here, a hydrostatic pressure that regulate water movement between the vascular compartment and the interstitial compartment. Water movement between the extracellular and intracellular compartments is dominated not by Starling forces at all, but simply by gradients and osmolality. And the movement of water bidirectionally through aquaporin channels always serves to equalize the osmolality on either side of this cell membrane. So, back to the case of the day. The Cezine marathoner, 45-year-old woman. She runs her first marathon after 6 months training. She has good time, pretty happy. She's rehydrated, but only with water. And she begins to complain about a headache and then rapidly becomes quite ill. And then has dramatically a seizure and has to be taken for medical attention. Why can this happen? Well, excessive water intake in the absence of solutes. Now, how can we understand that? Well, excessive water intake will lead to a decrease in the sodium concentration in the extracellular space as she's jogging along. it will lead to water movement into cells. So in the tent, when she was looked at, the first thing they noticed was that when she's drinking water, that her sodium concentration was dramatically reduced. Why? Because sodium, of course, is restricted to the extracellular space, and she was drinking water. Water was diluting the sodium concentration. That dilution of the sodium concentration lowers the osmolality. The low osmolality means that there's now an osmolar gradient between the extracellular space and the intracellular space, so water moves from outside of the cell into the cell. So water crosses the cell membranes from the extracellular space to the intracellular space. What is the consequence? Well, remember when we looked at that slide of red blood cells when we drank water? The brain cells swell, just like those red blood cells. Intracranial pressure, because the brain is contained within the cranium, a bony cage, if you like, when the brain cells swell, the pressure rises, and that leads to neurologic dysfunction associated with seizures early on, headache and nausea as symptoms, seizures, eventually coma, and can actually lead to death. So, common in women with a slow pace. Why would that be? Well, they have a lower body weight. Lower body weight likely means lower muscle mass, a lower total body water content because of that lower body mass. And the slower pace means that she's regularly drinking more and more water as she moves around, as she moves through the marathon course. Consequence, well, because she doesn't have a very large total body water, and she continues over an extended period of time to drink water, that will lead to a more dramatic decrease in the sodium concentration in her extracellular space, and that will lead to a low osmolality and a movement of water into cells. The brain cells are most affected because indeed they have no room to expand because of the bony cranium that surrounds the brain. So what's the treatment? Well, the treatment they would do is a rapid infusion of concentrated saline. And you can imagine, what does that do? Well, that, if you go back to the second slide that we looked at with the red blood cells, if you now load her extracellular space with sodium, you raise the osmolality. That increase in osmolality will serve to pull water out of the cells. And as you pull water out of cells, the volume in that cell will decrease. And since the volume in that cell decreases, the pressure in the intracranium in the brain will decrease, and brain dysfunction will improve. And she'll go from having seizures, coma, backwards towards recovering relatively quickly. And you can do that quickly because her problem just occurred over the 5 hours of a race. So, key points from today. If you remembered nothing else from this lecture, I'd like you to remember that the total body water is about 50 to 60% of your body weight. The second thing I'd like you to remember is that 2/3 of your total body water sits in the intracellular compartment, and 1/3 sits outside of cells. What are the rules? Sodium is primarily restricted to the extracellular fluid compartment. Water crosses cell membranes bidirectionally on the basis of osmolality and particularly an osmolar gradient. The plasma and interstitial volume depend critically on the balance between hydrostatic pressure and oncotic pressure. Hydrostatic pressure conferred by the heart, oncotic pressure conferred by the synthesis of albumin in the liver. Now, for the next lecture, we're going to begin to introduce the kidney and how the kidney interacts with these extracellular fluid compartments and the constituents of those fluid compartments to regulate total and maintain normal body homeostasis. And this is the case of the day, which I'll let you read between lectures. That's going to help us focus on the first function of the kidney that we'll talk about, and that is the glomerular filtration rate. So thanks very much. I'll see you at the next lecture.